Hello everyone, this is Yao and I'm presenting my final project of AAE654 about simulating shattering of tempered glass. And the geometry and boundary condition physical properties are for the goal of simulation. We need to inspect on extremely fragile material about the fracture mode, crack and propagation, and fracture toughness, and how the crack propagate within the geometry. And for the geometry, we have a piece of tempered glass of 50 by 50 by 6 millimeter. The thickness was set because of the industrial standard. So the tempered glass should not be qualified if the thickness is under 6 millimeters. And then for this specific model, I can get more comprehensive, but not all-inclusive data for modeling the material. And the load for the material is the ultimate tensile strength on the top and bottom edges with 14.5 megapascal. And the constraint is clamped at the left edges for no movement and no rotation. For the project, I use 3D geometry instead of 2D because 3D is really more comprehensive. And for the exam 2, I want to compare to how it developed against a simple assumed plane stress 2D model. And the 3D mesh, I use counter integration for the stiffness calculation, and I need reinforcement around the crack to solve the convergence issue. And XFEM is used for cracks development inspection. And the material property is as follows. So tempered glass is really similar to aluminum in some way, but is really sensitive to crack. And the crack will develop very quick because of the high internal stress. The stress intensity factor, or SIF, and the J integral. So for the model, J integral was used for calculating the stress intensity factor, and it goes both ways. So Abacus can output the J integral as a result, and we can also have the SIF as result, and then estimate the J integral. They are the same in the bulk part, but a slightly different. I will discuss it in the results section. And the result for the simulation is the intensity factor is 2.388 megapascal by meter square root, and mode 1 intensity is the same as mode 2, but mode 3 is 0 since we have no autoplane shear. And J integrals can be very different, and I will talk about it later. So crack propagation. We see the J integral is arising, and I can play a little clip about how it develops. So as we can see, the intensity increases as the crack develops, and then it was going in the way that is predicted. And the crack was initially set to 10 millimeter, and it was expandable. With KIC larger than K from the literature, that is 1 megapascal per square root meter, and crack propagation is expected. And the crack developed to 20 millimeter before convergence issue occurs. So for XFEM, convergence issue is really hard to solve. Although I use different reinforcement around the crack predicted development pathway, a convergence issue is still occurring, but the result is already significant enough that proven the model is valid given with a proper physical data. And the FEA result versus reality. The results are very far beside there is no out-of-plane shear crack. And the FEA result is roughly 2 times the reality. Also for the crack tip stress that we calculated using the formula given. The result is consistent and as expected because the internal stress was assumed to be evenly distributed, and then external stress was applied with the model not over constrained. So the result is not consistent with the literature, but the FEA result is consistent, and the stress field is very similar to the book has intended to be, as the kidney shape, as we can see from the lower right. And the J integral calculated is slightly below the J integral estimated from the output of intensity factor. This is expected because the algorithm is different, and then for the random error and the step error and then passing on variables is expected, and then the result is acceptable but not ideal. So the overall analysis is we put a sample of tempered glass for analysis, and SIF is directly retrieved from the counter integration 3D model with mesh reinforcement around the track as the requirement. And J integral was calculated and estimated using the SIF. And crack propagation and path development is calculated using XFEM with mesh reinforcement around the predicted path. And the result is not satisfying because it doesn't line up with the literature. But given it's really hard to obtain any physical property from such a fragile material with such high internal stress, it is proven that the model is working, but we need a more accurate model of the material to get it to produce accurate result. And the T stress is less than 1, so plasticity around the crack exists. So the limitation and the criticism is the material is really hard to model, so the damage evolution model is not accurate. And internal stress might not be uniform and it's really hard to measure. And with all the manufacturing defects and all the random errors occurred in having the sample ready, it's really hard to determine whether the sample is representative or not. And since material is really sensitive to crack, there is barely any way to obtain the physical property with the experimental method. And since the pressure we loaded is uniaxial, but in theory, it's more like to be a radial 3, maybe not 3, but bidirectional loading. The simulation can be improved. And here's my reference. Thanks for the semester, and yeah.